Greetings, this is the answer key to learning targets and sample questions practice test for test number 2. So the first problem, there are blank moles of carbon atoms and 4 moles of dimethyl sulfoxide. So 4 moles of it, and there are 2 carbons, so 4 times 2 is 8 moles. Question 1, molecular weight of methanol rounded up to the nearest integer, 12 for carbon, 3 for the 3 hydrogens, 16 for the oxygen, 1 for the other hydrogen, just going in order right here, about 32 grams per mole. Mass of 4 moles of C2H4, 4 moles, we're going from moles to grams now, add up C2H4 on the periodic table, 28, 4 times 28, 112 grams. Number 3, mass of 1 molecule. In 1 molecule, we're going to go from molecules 2 moles, and then from moles 2 grams. So right here is 1 molecule, and in 1 mole there are 6.02 times 10 to the 23rd molecules, and since it's C2H4O, then it adds up to 44 grams per mole. So 1 divided by 6.02 times 44 ends up to be 7.3 times 10 to the negative 23rd grams. Next one, moles of carbon dioxide and 22 grams of carbon dioxide. 22 grams, we're going to go from grams to moles, so grams on the bottom, moles on the top. There's 44 grams in a mole of carbon dioxide, 0.5 moles. And then number 5, how many grams of hydrogen are in 16 grams of CH4O? A couple of different ways to do this one. The way that I chose to do it was to find the percentage of hydrogen in CH4O. So part divided by whole, 4/32, so 12.5%. And then I took that percent times 16, because 16 grams total. So 12.5% of it is 2 grams of it. There are other ways to do that one as well, but that's just one way. Next one, what is the empirical formula of a compound? So for the steps for empirical formula, step number 1 is to assume a 100-gram sample. So I did that here. I've got 40 grams, 6.7 grams, 53 grams. Convert to moles, 12 grams per mole for carbon, 1 gram per mole for hydrogen, 16 grams per mole for oxygen. Now I've got the number of moles of each in this assumed 100-gram sample. Next, divide by the smallest. The smallest of these is 3.33, and now I get my simplest whole number ratio of 1 to 2 to 1. So CH2O turns out to be my empirical formula. Question number 7, the mass percent of oxygen in carbon monoxide. So first you have to be able to write carbon monoxide. Carbon monoxide is CO. And then you take the part divided by the whole. So the percent oxygen would be 16 divided by 28, because carbon monoxide is CO and carbon is, well, they asked for the percent of oxygen, I believe. So that's 16 on the periodic table. You add the C and the O together, you get 28 times 157%. Then number 8, CH2, molecular mass of 28. What is its formula? So if we know that CH2, when we add it up on the periodic table, is 14 grams, and the molecular formula is 28 grams total, something times 14 has to equal 28. So I wrote it as 14x equals 28, x equals 2, so that means I need to double each of the subscripts. So it becomes C2H4 as the molecular formula for that. Okay, going on, number 9 asks for how many moles of O2 are produced. These are stoichiometry problems now. And so in this one, we take the number of moles that we have, multiply it by the ratio of oxygens to KO2s. You can see from the balanced chemical equation there's a 4 here and there's a 3 right here. And so I end up with that number of moles. Next one, how many moles can be produced? So we have 6 moles of this guy and 9 moles of this guy, and it even says, hint, there's a limiting reactant. So to determine the limiter, remember, take your number of moles that you have, divide it by the coefficient, and whichever one's going to end up being smaller is your limiter. So 9 divided by 3 is 3, that's smaller than 6, so work based on the limiter. So I take my limiter, 9H2s, and then from the balanced chemical equation, it's a 2 to 3 ratio for ammonia to hydrogen right here. So it ends up being 6 moles of NH3. And then number 11, bonus, calculate the number of excess remaining. So to find the excess remaining, you still have to start with your limiter, and your limiter is hydrogen. So we start with 9 moles of hydrogen, and now we compare it to the excess reagent. The excess reagent is N2, and if you look at the balanced chemical equation, once again, there are 1 nitrogen for every 3 hydrogens, so that's why I wrote 1 nitrogen on the top, because that's my desired unit. I want to find out how much of that I'm going to use to 3 hydrogens. So 3 of them are used up. I started with 6 nitrogens, I used 3 up, so 3 moles remain. Going to the next page, backside, a bunch of electrolyte type questions. Notice they give you some information here in the learning targets. You should know that sodium, potassium, ammonium, and nitrate species are soluble. It says you have to have that memorized, and it's really helpful if you do, but it's also on the front of the test, so you have to recognize those right away. An electrolyte conducts electricity because it has ions, or positive or negatively charged particles. Strong electrolytes do. Weak electrolytes have some of those. Non-electrolytes don't have any, so they wouldn't conduct electricity. What is an electrolyte? It's a dissolved species that forms positive or negatively charged particles. What's an ion? Same thing. Ion is something that has a positive or negative charge. It gained or lost electrons. Differentiate between a cation and an anion. Cations are positive, anions are negative. Which are soluble, which are not. So you need to use the solubility rules, which are simply given to you right up here. You don't need to know any other ones other than these. You can see here's a potassium containing salt, so it's soluble. Sodium containing salt, so it's soluble. Here, this one isn't talked about by any, so it's insoluble. Nitrate containing and ammonium containing, so they're soluble. Aluminum hydroxide would be insoluble because it's not talked about in any of these 4 rules right up here. Are strong acids soluble? Yes, and strong acids also dissociate completely. Strong acid bases soluble? Yes, and they also dissociate completely. So not only do they dissolve in water, but they split up into their ions. If something's soluble, does it mean it's a strong electrolyte? Not necessarily, no. Sugar, for example, dissolves in water, but it doesn't split up into ions because it's a non-electrolyte. So it's only a strong electrolyte if it dissociates or breaks up completely. What's an acid? An H plus donor. What's a base? An H plus acceptor. Defining oxidation, define reduction. Oxidation is the loss of electrons. Reduction is the gain of electrons. I like to think of it as up is oxidation, down in charge is reduction. So then you can look from left to right on a reaction and decide which thing goes up in charge. That's your oxidized species. Which thing goes down in charge? That's reduced. Which of the following are strong electrolytes? Well, Hickel is, because it's one of the strong acids. NaCl, strong electrolyte, because it's a soluble ionic salt. H2SO4, strong electrolyte, because it's a strong acid. KOH, strong base. Solution of potassium chloride exists primarily as K plus and Cl minuses. Once again, it's a soluble ionic salt, so it completely dissociates. Type of reaction is this. You can see there's a base right here, SROH2, and there's an acid, HBr. So it's going to be an acid-base reaction. Type of reaction is the following here. This is a decomp because it breaks up into 2 or more species. Type is this. This is a precipitation reaction. A simple way to tell that is because it forms a solid right here. Here's a redox reaction because you can see that silver changes from +1 to 0. Cadmium changes from 0 to +2. And this one, predict the products right here. Nickel and bromine will go together to make NiBr2, or you could guess that nickel is going to be a +3 ion and make it NiBr3. It doesn't say you have to balance it, so you'll have to make an educated guess on that type of problem. What dissolved species are in solution? You're going to have potassium ions and you're going to have carbonate ions, so letter B. Which element is oxidized and which one's reduced? To find this out, you have to go through and assign the oxidation numbers, so I'll do that really quickly to help you through so you can remember the rules that you have to know. First of all, the easiest way to do this one is to pick your weak animals. And I know that nitrate right here, nitrate has a -1 charge overall. Okay, and there are 3 of them in here. And then manganese plus -3 has to add up to 0 because there's no charge up in here. So that means manganese must be +3. Magnesium right here is 0. Manganese over here is going to be 0. And then once again, you have your nitrate species, which is -1, and there are 3 of them right here. I'm sorry, 2 of them. 2 of them right here. And that means magnesium must be +2 to balance out that -2. So look at what changed. Magnesium went from 0 to positive true. It went up, and therefore it's oxidized. Manganese went 3 to, right over here, to 0, and so that went down in charge, and down is reduced. So I can see that my magnesium is my oxidized species, and manganese is my reduced species. Going on to the next page, number 28, which does hydrogen have an oxidation number of +1? Remember, hydrogen is always +1 when it's with a nonmetal. So here it's with a nonmetal called oxygen, so it's +1. Here it's with a nonmetal called chlorine, so it's +1. Here it's with two nonmetals, carbon and oxygen, so it is +1 as well. If you look at this KH right here, here's where H would be -1. And H2 right here, of course, it's alone by itself, so it would have a charge of 0. What's the oxidation number of sulfur in this one? So in H2SO4, know that oxygen is a -2 charge. There are 4 of them. Sulfur must be some charge. I don't know what it is. Hydrogen, when it's with nonmetals, is +1. That was just the last question. So 2 plus something plus -8, and it has to add up to whatever it says in the upper right-hand corner here, which is 0. So that must be +6 that it has to be. So +6 is my answer right here. Which element is or are reduced, and which is the following reaction? So you have to go through and assign oxidation numbers again. You can go ahead and do that, and you'll find out iron is reduced, as carbon is oxidized. Which is our spectator ions in this? So for these types, you have to go through and you have to split them up and then decide which one just goes away. Since this is a pure solid, keep it together. The H plus and the Cl minuses will split up because it's a strong electrolyte. Over here, the chlorides are soluble. It tells you that all chloride ionic compounds are soluble except for. So split this guy up into Ti plus 2. I forgot the arrow right here. And it's going to be 2 Cl minuses. And then I have H2 gas over here by itself. So you can see which are the spectator ions. Well, the things that cross off are the chloride ion and the chloride ion right here. So those are the ones that would be the spectator, and so I chose chloride right there. Well, I wrote it down. Which are spectators in this one? You do the same thing, split it up, and you'll find out that the Na plus and the Cl minus end up crossing off. And for this one, write the net ionic equation for this one. So do the splitting up of the potassium carbonate and then magnesium nitrate. And then over here, it's going to swap the cations. The potassium goes together with the nitrate, and the magnesium goes together with the carbonate. Don't forget this is +2, -2, so they actually cancel each other out. This is +1, -1, so they cancel each other out. Balance the equation, you end up with a 2 right here, and now you got to go through and split them. So you know that all potassium salts are soluble, so it's going to end up being 2K plus and the CO3 2 minus. This guy right here is the Mg plus 2 and 2 NO3 minuses. Over here on the right hand side, this is soluble, so 2K plus 2 NO3 minuses. And then magnesium carbonate is just MgCO3. So what casts off? The potassium, the nitrate, the potassium, and the nitrate. So those guys and this guy right here are your ions that are going to make the magnesium carbonate. Next page, I can calculate stoichiometry problems, dilution problems, and then molarity problems. I have these worked on a separate page that we can take a look at step by step. The first one are titration problems, which are a form of stoichiometry problems. They follow the same 4 steps as all stoichiometry problems. So first, write the balanced chemical equation. Second, when in doubt, convert to moles. In this case, we'll use the molarity triangle to do that. Mole to mole ratio, and then convert to the asked for units. And the units they're asking for are milliliters all the time right here. You can see that in the question. Sometimes it's nice to work these problems backwards and look first in the question, what are they really asking for? Where am I going to convert to? Do they want liters? Do they want milliliters? What do they want? So in 34, you can see that we've got 30 mils of 0.5 molar, and then in the end it's going to be a 2 molar solution. So first, write the balanced chemical equation. Second, convert to moles. Liters times molarity. So there's my moles right here. Next, mole to mole ratio. It's a 1-to-1 ratio between potassium hydroxide right here and hydrogen iodide or hydroiodic acid. And then convert to the asked for units. They want liters. So I'll take my moles right here and divide it by my liters. So this is my moles. Divided by my molarity, I'm sorry, divided by my 2 molar solution. How do I know it's a 2 molar solution? I look back here in the question, it says it's 2 molar right there. And it ends up being 7.5 milliliters. I'll zoom this out so you can see the other 3 problems. I'm sorry, the other 2, 35 and 36 are just the same as this problem, just different numbers. So here's 35 and here's 36. Similar type of problem where you write the balanced equation, convert to moles, 1-to-1 ratio, take your moles divided by your molarity, you'll get your answer in liters, make sure you convert it to milliliters. Okay, next set of questions, these right here are dilution problems. You can see that it has the word diluted in it, diluted in it, diluted in it, so then you know that this is going to be the kind that is in M1, V1 is equal to M2, V2, or MIVI is equal to MFVF, okay? And in the first problem, they start with a 2 molar solution, and it's a 0.2 sample, and you're going to dilute it to 1 liter. Okay? So M1, 2 molar, 0.2 liter, MF, 1 liter. So solve for MF, you get 0.4 molar. The next 2 problems are exactly the same, and so I just did the math for you here, and that's 38, 39. Okay, problem 40 is a solution preparation problem so it uses the molarity triangle. And so I did the work on a separate page again too, and you're going to use this molarity triangle to help solve all 3 of these problems, and they're almost always all the same. So the first one, it says 20 grams of sodium hydroxide are in water, or half a liter. What is the molar concentration? So I'm looking for capital M right here. I got to find the number of moles and divide it by the liters. First, when in doubt, convert to moles. Take your 20 grams, divide it by the molar mass added up on the periodic table. If you add Na and an O and an H on the periodic table, you get 40, so you get 0.5 moles. And it says it's going to be a half liter of solutions, or 0.5 liters of solution. So divided by 0.5, you end up with a 1 molar solution. 41 and 42 are very similar. They just give you a different grams of sodium hydroxide, and they also give you a different number of liters. So I worked those next problems, 2 problems right here, and you can see 41, convert to moles, divide by your liters, convert to moles, divide by your liters, and you got 41 and 42 done. The next part are free response questions, and I'm going to put those on a separate video. If you want to take a look at the fill in the blank ones here for the balancing for question 1, we'll pick up with the free response questions on a separate video after this.